that I am seen much. Okay, go. Good morning, everyone. My name is Mahsa, and on behalf of my co-authors, Fulya, Professor Koch, and Professor Abrahamczyk, who is not here, unfortunately, I want to present to you our mixed reality application that we developed last year for holographic structural analysis experiments. So our main motivation comes from virtual, augmented, and mixed reality applications in education. And that's because there has been an increasing demand in digitalization in the past decades, which is good because in modern teaching practice, we get some benefits from it. For example, we get decentralized learning environments. So regardless of where the students are or which platforms they are using to some extent, they still have access to the classroom. We can integrate learner-specific tools. For example, we know that not all students have the same learning speed, or some students suffer from some learning disabilities, such as dyslexia. And we can also integrate flexibility in times of crisis, such as the recent pandemic. And then, for that, we need to integrate also modern learning objects. And these learning objects mainly have many characteristics, but mainly we focus on interoperable and reusable learning objects. And we wish to have more interactions with students all the time, so yeah, to make it more interactive. And above all, most recently, the immersive environments have been also used widely in teaching, in modern teaching practice. So with that in mind, we thought about why not using holograms as learning objects, because it has been widely used in different disciplines. For example, in healthcare system or medical education, or for example in army trainings, or for example in engineering disciplines such as aviation and automation. But our focus is the experiments in structural engineering, because we have to provide the remote access experiments to students as a part of the curriculum for civil engineering, because you know, all of you, that we are not supposed to just deliver seminars and lectures, because lab experiments play a key role in teaching in civil engineering. So we thought that we go with the mixed reality application, and we wanted to test the potentials. And we had some objectives. Above all, we wanted the experiments to be user-defined. So we wanted to make it more interactive for the students. We wanted to benefit from inverted classrooms concept. And we know from the literature that game-alike experience is very effective. So with respect to learning objectives and with respect to making the assignments fun. But we also, since we were testing the potentials, we just put the focus on basic structural definitions and analysis methods. And for that, we needed to find the suitable tools. And that's why we know that for using the holograms, we are platform dependent, we are device dependent. But to make it more accessible for students, we just didn't use Microsoft HoloLens head mounts, but also we decided that we want to make the app available for smartphones. And since we want to make it interactive, then we have to use parametric modeling tools so that we can manipulate the parameters and we can give this option to students so that they can play around with the experiment. And for that, we use Grasshopper, which is a plugin for Rhino 3D software. And this, the Grasshopper environment has different add-ons, some proprietary add-ons which are already there with predefined elements. And there are different add-ons that you can purchase, or some of them are also for free. But what we have used here in this project is the FOLOGRAM add-on on Grasshopper, because FOLOGRAM offers the option so that you can sync the holograms with your parametric model. And FOLOGRAM also offers the app on the device, so you can sync your device with the parametric model, and we can view the holograms in real time, and any changes is transmitted. And the second add-on that we have used is the Karamba 3D, which offers the parameters for doing the structural definitions and structural analysis. So if I want to give you an overview of what's happening in the parametric model and in this application, is that we have on one side the parametric model on the PC or on the laptop, and on the other hand we have the devices, either HoloLens or smartphone. And FOLOGRAM in between plays a role for synchronizing the objects, the virtual objects, and Karamba is there to make the definitions for the model. But what comes in the beginning is that, okay, overall we have 4 phases, which I'm gonna explain next. And here in this diagram, you can see this loop between the parametric model and the device. So the first phase is the spatial mapping. So as soon as the FOLOGRAM app is loaded on the device, the device starts to register the meshes and scan the environment where the student is. And it can be used both in closed and open areas. So the only criteria is that the room should be bright enough so that we can register the meshes correctly. And we always recommend the students to move around the point of interest if they are, especially with the smartphone, because the HoloLens has better sensors and can track the meshes better. But with the phone, we always tell them to go around and go forward to get closer to the points of interest so that they can make a good precision for the registered meshes. If the user is not happy with the registered meshes, there's a reset button, which will reset the parameter which is collecting the mesh. And as soon as the scanning is done, and as soon as we are seeing it in live, which meshes are already registered on right now. So as soon as we say, okay, it's fine, then using the drop-down menu, the student can move to the next phase. The second phase is point selection. And for point selection, we have the option whether to select the points in the space within the area of the scanned meshes, or to snap the points on the surfaces, the scanned surfaces. And since we had this objective that we want to overlay the virtual objects with the real objects, the snapping point mode was more interesting and more important for us. For example, the point alignment on surfaces is also dependent on how good the meshes are registered. But for ease of visualization and for visualization purposes, in this mode, we have defined some holographic spheres so that when the points are selected, the students can see them, and they can move around and they can see whether the points are aligned on the surface or not. And the number of points which students have to select is dependent on which mode of experiment they are trying. For now, we have 2 modes, beam experiment and frame experiment. So if they are in the beam experiment mode, they need at least 2 points. And then afterwards, if they have registered more points, they can filter out which points to keep and which points to delete. The same applies to the frame mode, with the difference that in frame mode, we need at least 4 points to be selected. As soon as the points are selected, then they can rearrange the points, they can see the labels, the node number of the points, and then they can move to the next phase, which is model definition. And in the next phase, from now on, everything is set. So they cannot make any changes in the meshes or in the point selection. And here, now we are using the Karamba 3D elements for defining the parameters. And on the right-hand side, you see the parameter menu, which is synced on the hologram. And the students here can manipulate and can change the parameters. They can define the type of cross-section that they want, the material, They can select the supports and degrees of freedom for the nodes. And they can also define the loads. So we have different types of loads. We have the gravity, we have distributed load, and we have point loads. And for the point loads, for these loads, they can choose the value of the load, and also the location for the point loads. And as soon as they have changed, they have included the changes in the parameters, the model is assembled and is ready for model analysis, which is the last phase. And in the model analysis phase, we have, for now, integrated linear first order and second order analysis. And what happens here is that the model view definition exports the result of the analysis as meshes and curves. So the curves correspond to the internal forces diagram, and the meshes can visualize the cross-section and also the surface underneath the, for example, the bending moment and the shear force diagram and such. Parameters such as maximum bending moment and shear force can also be visualized as holograms, as name tags, and we can toggle them on and off for better visualization. And also, on the right-hand side, you can see that when you are far away from the hologram, you cannot really distinguish between the deformed shape or between the internal force diagram. That's why we have integrated also the scaling factor, that they can, the student can increase the scaling so that they can visualize it better and they can see it better. Okay, what have we learned and what's next to come? Unfortunately, last year we couldn't force students to try the app, to come to the lab and try the app, so we had a very limited number of students who tried. But we distinguish between the students who have tried it on the smartphone and who have tried the HoloLens. Our focus was the integrity of the app with respect to whether our learning objectives are met, and whether if it's, for example, interactive enough, whether the students are happy with this experiment, if they have learned something new, or is it just for fun. And they all were happier, so to say, with HoloLens, and we could exploit the full capacity of the mixed reality app, of course, with HoloLens, because we could use all the hand gestures, and we could integrate also more functions with respect to each hand gesture and stuff like that. There are still two drawbacks with respect to the application, and it's that we are device dependent, and the licenses that we use for the software packages that we are using for developing the MR application are not cheap. So probably not everyone can try it. And for further improvements for what comes next, we would focus on the comfort. For example, we have to redefine how we are visualizing our parameters menu, how the students can navigate through different parameters, and how can they manipulate the parameters easier. We definitely need to integrate more experiment modes. For example, we can define truss structures, and we can use shell elements as well. And we can also integrate more analysis modes, for example, nonlinear analysis modes, or we can also define our script and we can integrate it into the parametric model. And last but not least, we have to extend our survey, and we have to make it more consistent with respect to the e-learning objectives. And we have to make it in a way that we can track the student performance, especially when we have some predefined assignments. We want to know when they start the application and how they perform step by step, how many times they have to re-register the meshes or the points, or how fast can they submit an assignment. That's all from my side. I'm looking forward to your questions.